Okay, so we're back. We're going to talk about amino acids and the proteins that they make up. And really, what we're going to talk about the next couple topics will be proteins, carbohydrates, and lipids. And what we're going to talk about with those is the structure. Function follows structure, so we've got to have a grasp on that structure. A lot of our time, particularly next trimester, will be spent on looking at the proteins, the carbohydrates, and the lipids as fuel molecules. That's not their only purpose. It's one that we do spend a significant amount of time on. We'll spend some time on proteins in other capacities, performing other functions. For example, in anatomy, you're going to see a lot of proteins. They are structural molecules. They make up or partially make up tendons, cartilage, hair, nails, muscles. I guess that's more of a contractile function. We're going to talk about hemoglobin as a transporter. So it's a protein that transports oxygen among other things. Oxygen is the molecule we think of most often. We've already seen hemoglobin as a buffer. In other classes, you'll talk about milk, the proteins it contains as a storage molecule. We'll talk about hormones. We're going to talk about insulin in this class. We'll talk about it again in endocrinology. We're also going to talk about growth hormone. We're going to spend a ton of time on enzymes. Like we said when we were talking about enzymes are proteins. So it's a big role, big thing that they do. Immunology will talk about proteins in your immune response. So you're going to see them a lot of different places. Okay, let's talk about amino acid structure for a minute. Conventionally, and we're going to go through some drawing, really we're going to draw the same thing a few different ways. So with an amino acid, we have a carbon in the middle, we have a side chain, an R group. R is the variable, like the X in math is the variable. So we have a hydrogen, we have a carboxylic acid attached and properly drawn, spelled out, that's it. And we have an amino group, properly drawn, spelled out, that's our amino group. So this is our amino group. This is our carboxylic acid. And the amino group and the carboxylic acid are functional groups. We'll come back and talk about what functional groups are. What they are, or we'll get into the particular ones, what they are is a name for a particular arrangement of part of a molecule. So like here, rather than saying over and over and over, I have a carbon double bonded to one oxygen, single bonded to another, which is single bonded to a hydrogen, over and over, I'll say I have a carboxylic acid. And you know that's a carbon double bonded to an oxygen, single bonded to another one, single bonded to a hydrogen. And we're going to learn those. So we'll do a section where we learn those. Same thing here. Rather than saying I have a nitrogen single bonded to two hydrogens, I'll say I have an amino group. So with those groups, this is spelled out 100% properly to every single detail. But chemists don't typically do that. What we have a tendency to write is we'll put the carbon in the middle, the hydrogen, the R group, we'll talk about it in a minute, and go COOH. We'll also go NH2. And if you don't know what that means, it looks like I have oxygens attached to each other, hydrogens connecting a nitrogen to a carbon and stuff like that. I don't. But you have to know that this translates to this translates to this. So kind of our, I don't know, can I say lazy way of doing it? I guess I can. But our shorthand way of doing it might be a better thing to say. All right, and let's go back to this R group idea. The R, like we said, is like the X in math, and it's our variable. So the family is amino acids. So every member of the family has this part the same. Like everybody in your family, all your brothers and sisters, say, have the same last name. Then the R group is different, and that's what makes each member of the family, each individual amino acid in the family of amino acids, different. So you have a different last name than your brothers and your sisters, and that's how you're identified as you as a member of your family. So that's the R group, the variable. The properties of the different amino acids, which we'll come to later, are determined by this R group. Like saying you have, I don't know, red hair, blue eyes, and big feet, whatever. Those are your characteristics. So you're described by your name, and you have your characteristics. Your brother or sister has their characteristics, and they're described by their name. So that's the R group. What this alpha carbon thing is something we'll come back to. And let's do it quick since it is marked here, but we'll get into it in more detail later on. So the alpha carbon is the carbon next to the carboxyl carbon. So we call this carbon the carboxyl carbon. Because it's part of the carboxylic acid, and then we start counting. So the one next to it is the alpha carbon. We add another one to be beta, and so on. When we have fatty acids and a chain of carbons, we'll be able to do more with that. So that's our amino acid structure. So like we said, depending on what the R group is, that makes it whatever amino acid it is. If it's just a hydrogen, that's a glycine. Just a little methyl group, that's an alanine, and so on. We're going to go further into this, talk about which amino acids have branched chains as their R groups, have sulfur in their R groups, things like that. Okay, again, depending on what that R group is, that determines the characteristics of that amino acid, such as we might have just carbons and hydrogens and have a polar amino acid, or a nonpolar, I'm sorry. We might have oxygens or nitrogens in there. We're going to start saying things like oxygens are big electron hogs, because they are. And we'll talk about the implication from that. So, amino acids can act as either an acid or a base. And kind of coming back to the buffer definition too, we have a molecule that, well, the buffer definition, we can take a hydrogen ion off of one end, off of that COOH, or we can put another one on to the amino end, turn the NH2 into an NH3. So there's a couple of names for that. I didn't mean to cut it off here. All right, we'll do it wherever. So a molecule that has that capability of acting as both an acid or a base is called a Zwitter ion. Not too awfully likely you'll see that term. It's also called an ampholyte. It's a synonym. Not too terribly likely that you'll see that term, but the adjective for that is amphoteric. It's an amphoteric molecule. Higher probability of seeing that one. So an amphoteric molecule is one that can act as an acid or a base. We have 20 naturally occurring amino acids that we're going to be worrying about, and we'll come back to the characteristics of them. I know some of you are looking at this and saying, oh no, do I have to learn that again? Yes, but I have a more systematic way of doing it than what we're doing here. Okay, I try to keep your definitions to a minimum. I'm not always successful at that, but I'll keep trying. So what a protein is a chain of amino acids. And we're going to talk about what I mean by a chain. Well, I mean a chain, but how that chain is formed. What kind of bonds connect those amino acids. But if we have a short chain, like less than 40 or 50 amino acids, we're going to call that a residue. Bigger than that, we're going to call that a protein. So let's talk about something with questions. My first thought would be, all right, well, if you ask me 45 amino acids, what do I call that, a residue or a protein? You're pretty safe that no one ever asks you that. They'll say 20 or they'll say 1,000 or something. So it's not terminology that's used an awful lot, but when you do get asked about it, people who are writing the questions are usually pretty good about staying away from the maybe this, maybe that kind of range. Okay, so let's jump ahead for a second, and then we're going to come back. So where we're going with all this is we're going to talk about the hierarchical nature of protein structure. So we have a chain of amino acids. So first, how are we going to make that chain of amino acids? How are we going to connect them in the first place? So I shouldn't have had that dash in there. So how am I first going to just connect that chain, form the chain? And we'll talk about that. And the answer to that is we're going to form the primary protein structure. Then, if I have this chain, can I make any other arrangement with it? I end up with this big chain. What am I going to do with that? Well, I can form something using hydrogen bonds. We'll talk about why we get the hydrogen bonds. But where we're going there is secondary structure. Then, when I form the secondary structure, I can do more folding and arranging, forming kind of a 3D structure. And a lot of this is forming structures with those side chains. That's going to be our tertiary structure. Then I might have multiple chains that all hang out together one way or another. That's going to be my quaternary structure. So we're going to go through each one of those step by step. So let's back up. First one we're going to look at is the formation of a peptide bond. So in a peptide bond, what I'm going to do is I'm going to have two amino acids side by side, and I'm going to join the carboxyl carbon of one to the amino hydrogen of another. So I have an amino acid, I have my amino group, carbon, R group, and my carboxylic acid. I have that I want to join to another amino acid. I have my amino group and then the rest of my molecule. So I drew out the carboxylic acid and the amino group on the ends where I want to join them. So what I'm going to do is, best way to think about it, or kind of easiest way to think about it, is I'm going to pull the water out. I'm going to get an H and an OH out of there. So by doing that, I can join I guess I should be consistent with my colors. We'll do a special peptide bond color. That's my peptide bond. So what I've done is I've joined my carboxyl oxygen of one amino acid to my nitrogen of the other amino acid. And I've done it with that red bond, my peptide bond. And then I end up with a water, also the H and the OH, the hydrogen and the hydroxyl that I took off of there. So this is my peptide bond. Okay, so a peptide bond characterizes our primary protein structure. That's how we connect one amino acid to another. So on each end, I can connect another amino acid, and so on. So here's the thing with a peptide bond. It's kind of an oddball little bond in a way. And what I mean by that is a few things. One is not really an oddball thing, but it's a covalent bond. So it's a true sharing of electrons kind of bond, a covalent bond by definition. It's not broken by the conditions that denature proteins. Denaturing proteins refers to breaking some of the other structures that we're going to talk about. If you do want to break it without enzymes, we're going to do it with enzymes, so it's easy to forget how to do it without enzymes. But if you want to break a peptide bond without enzymes, you're going to do it by raising the temperature and swinging the pH. So you're going to have to raise the temperature and then swing the pH either very high or very low. We can break some of the other structures by raising the temperature or swinging the pH. And like I said, you tend to forget this because everything we're going to do with enzymes. Okay, peptide bonds have a partial double bond character, kind of a loaded term. And what that means is it's a wannabe. So it's a wannabe double bond. And just like any wannabe, it wants to be, but it isn't. So it acts like a double bond in the sense that it's shorter than most single bonds. Remember, double bonds are shorter than single bonds. And it doesn't allow rotation. Remember, single bonds typically allow rotation, double bonds don't. So it's shorter and no rotation, which sounds like a double bond, but it's not. It's a wannabe. Remember, a wannabe isn't that thing. A wannabe just wants to be that thing, but it isn't. So the proper way of saying that is we have partial double bond character. Acts like a double bond, even though it isn't. We have some polarity in that bond, and we'll talk about that in a minute. All right, let's talk about naming amino acids. We're not going to do it, but depending on what you're reading, what research you're reading, and you need to be reading research. Let's do a soapbox moment for a moment. Start thinking about your niche. And what I mean by that is you have interest, you have stuff you like learning and doing and everything. Can you turn any of that into a niche for your practice? Really, really important that you do that. That's going to separate you from the chiropractor down the street, across town, whatever. And it's not that you or that other chiropractor are any better or worse than each other necessarily. You're just different. And you might have this niche that a particular patient is drawn to. So, I know we've talked about it already, but I want to remind you, get reading about it, get learning, become the expert in that niche. So, when you're reading, you might see an amino acid or a peptide, polypeptide named. It's named by the amino acids that make up that polypeptide. So what we do is we line them up with the amino group to the left and the carboxylic acid group to the right. Then we name them, kind of. So let's say we have glycine, lysine, phenylalanine, arginine, serine. What we would do is rather than saying glycine, lysine, We'll change the "ene" part, that "ene" ending. Remember we said amino acids a lot of times end in "ene." We're going to change the "ene" to an "ill" on most of them. So glycine will become glycyl. Lysine will become lysyl. Phenylalanine will become phenylalanyl, and so on, right up until the last one. The last one we're going to leave alone. So my little polypeptide chain that I've going on here is glycyl, lysyl, phenylalanyl, arginyl, serine. Leave serine alone. I'm not going to make you name them on any test or, give you a name and have you tell me what's in it. We made a deal, no naming, drawing, naming. But again, you're reading. You need to be reading. And you might come across glycyl, lysyl, phenyl, whatever. And I want you to be able to back it out and say, oh, it's a polypeptide chain made up of this amino acid attached to this one, and so on. Okay, so let's talk about cis and trans. We said we have these bonds that don't allow rotation, so we have functional groups attached to them, R groups attached to them, stuff attached to them. Back in organic chemistry, I'm just going to draw a double bond since it's typically what you see. Back in organic chemistry, you guys who took it, you learned about cis and trans. So you're going to have two functional groups or something attached to typically a molecule around a double bond. If those functional groups are across from each other, we call that the trans configuration. If they're on the same side, we call that cis. And then you would name the rest of the molecule. So let's think back to organic chemistry. When you were looking at questions about why this, why that, typically there were two answers to why. And this is one of those things you wish somebody had told you when you were in the middle of it. No one did. You figured it out after. So your two answers to everything just seemed like they were hydrogen bonding or steric effects. Steric effects, steric hindrance. If the question was why is part of a molecule pulled towards another part of a molecule or pulled towards another molecule, that was hydrogen bonding doing that. If it was why is something pushed away from something, that's going to be steric effects. So we're not going to worry about hydrogen bonding right now. We're going to talk about it a lot. But yes, steric effects definitely. Molecules like elbow room, they don't want all their parts on top of their parts and everything. They want to spread out, have elbow room. So if we look at our trans and our cis configuration, everything's spread out with more elbow room in a trans configuration. Cis configuration is kind of in its own way, on top of itself. So most of the time, including in amino acids, the trans configuration is going to be favored over the cis configuration. So most of the world is going to be in the trans configuration, including amino acids. So for you organic chemists, they're thinking everything's trans. You're almost right on that. And I say this a few times over and over and over because you'll second guess yourselves. And it's the organic chemist that will do it. And when you second guess yourself, it's always at the least opportune time, like in the middle of a test. There's one exception to trans being the favored configuration, and that exception is fatty acids. In a fatty acid, the cis configuration is the one we want. And this is where my organic chemist will say, oh, whoa, no, hang on. I don't like that. I don't like cis. I want my molecules to have elbow room. You do, and fatty acids do. In a fatty acid, we bend the molecule. So when we bend the molecule, we get these functional groups, or R group, or, well, not an R group, and a fatty acid, but we get whatever we need to away from each other by bending the molecule with fatty acids. So most of the world, trans is the configuration you want. Fatty acids are the exception to that. And I'll say that a few more times because the organic chemists start second guessing themselves there. Okay, so that was our primary protein structure. So our primary protein structures characterized by peptide bonds. Peptide bonds connect one amino acid to another to another. It's not supposed to look double, it just won't let me write over itself. We'll make them fat single bonds. So that's our primary protein structure. Next place we're going to go is we're going to go to secondary protein structure. Okay, so here's the way secondary protein structure works. We have this chain we just made. So we have this chain of amino acids. And along that chain of amino acids, we have carboxyl oxygens. So let's draw the whole thing out. Oops. Getting ahead of myself. Make our peptide bond medium blue, and then we'll draw the rest of the molecule in light blue. We are so color coordinated. Color coordinated biochemistry. Gotta like it. Okay, and then the rest of the molecule, more amino acids and so on. So we have the peptide bond, and we said already that oxygen is a big electron hog. So oxygen's a big electron hog, meaning it's going to end up having a little bit of a negative charge, or a partial negative charge. When oxygen hogs electrons, hydrogen's always the victim. So the amino hydrogen is the victim. It's going to end up a little bit positive. So it's going to end up with a partial positive charge. So what I end up with then is I have this chain of amino acids. So it's a big long chain, but because of this partial positive or partial negative charge on the oxygen, partial positive charge on the amino hydrogen, this chain ends up having all these little charges on it. So I end up with kind of picture a piece of string, but this really staticky piece of string. So I've got the chain, and I have all these little spots on it with partial positive charges and partial negative charges. So we can turn that string into some different shapes. It's kind of like if I have this piece of string with these charges, it's not going to just sit there all laid out, all flat, all pretty. The pluses are going to get attracted to the minuses. The minuses are going to get attracted to the pluses. So the structure formed by these particular hydrogen bonds between the carboxyl oxygen and the amino hydrogen is our secondary structure. There's three of them in particular we're going to talk about in order. One is an alpha helix, one's a beta pleated sheet, third one is a triple helix. Okay, so let's talk about an alpha helix first. So let's picture this. Let's say I have a piece of string. I have a very staticky piece of string. And I take that string and I start winding it around. Say I saved an empty paper towel roll from a roll of paper towels. And I start winding that string around that paper towel holder. So I have my paper towel holder. And I start winding my staticky string around. So I go around, go behind it, around, behind it. And so on. That's not as ugly as I thought it would be. So I wind it around, and what happens is I'll end up with a plus in the neighborhood of a minus. I'll end up with a minus in the neighborhood of a plus. Plus, minus, and so on. So what I'll end up doing is I'll hold the string to the next round of string, my next trip around it. So it takes 3 to 4 amino acids to go around my real helix, my real paper towel holder or whatever. So, but winding it around like that, I make what's called an alpha helix. So you'll see the term corkscrew shape, but just picture winding something around. I'm holding it in place by that partial negative charge on a carboxyl oxygen being attracted to a partial positive charge on an amino hydrogen, holding my string, every 3 to 4 amino acids, like amino acid number 1 will be attached to number 4 to number 8, so on, because it takes 3 to 4 rounds to go around. So that's my alpha helix. One of the things you're going to hear about an alpha helix is it's a very strong structure. Strong structure characteristic of fibrous proteins. But let's talk about strong for a minute. So when I say strong in reference to my alpha helix, I mean tensile strength. So let's picture a pencil. Say I'm sitting here holding a pencil right now. Let's say I grab both ends of the pencil and try pulling on it. Am I going to be able to break it? No. Probably you strong guys aren't either. Because what I'm doing is I'm pulling on it, I'm applying tension, I have high tensile strength. That's the kind of strength that my alpha helix has. I can pull on both ends, and I'm probably not going to break it. However, don't confuse that with shear strength. So now let's go back to my pencil again. Let's say I'm sitting here with the pencil and I want to try to snap it in half. Can I do that? Probably. Even I can do that. I know some of you are doubting me, but yeah, I could snap a pencil in half. That's shear strength. The pencil has a lot more tensile strength than it does shear strength. So my secondary structure, my alpha helix, has high tensile strength. My point right now is when you have a molecule and somebody says it's a strong molecule, think about strong in what way. In this case, it's strong in terms of resisting tension. Okay, so the next one we're going to talk about is a beta-pleated sheet. I don't know which slide to talk about this on, but whatever, we'll pick up. All right, so what I'm going to do this time is I'm going to take that polypeptide chain and I'm going to kind of wind it back and forth. And what's going to happen is I'm going to have my little pluses. Let me change the color. I'm going to have my little pluses attract to little minuses, minuses to pluses, and so on. And that's going to hold my configuration in this back and forth way that we just drew it. So it's the same thing, carboxyl oxygen to amino hydrogen. And I'll have all these pluses and minuses, and so on, just holding this whole thing together. When we're in class, I usually describe it by rows. And we'll have the rows of you guys. sitting in your rows. We'll say those are your desks. And a good friend of mine used to teach this class at the former New York Chiropractic College. And what she would do is she'd have the front row stand up and face this way. Second row stand up and face the other way. Next row stand up and face that way. And she would say your left hand is your carboxyl oxygen, your right hand is your amino hydrogen. So by orienting you guys like that, we'll put another row and have them face that way, she would have you hold hands. So you would hold hands left to right, and so on through the rows. So you would get this connection, forming the beta pleated sheet, kind of like we did here and everything. Where the pleating comes from is the fact we have one row facing this way, so facing this way, next row facing this way, and so on. So that's going to give us the effect of the pleating, the pleated appearance on the surface of a beta pleated sheet. Better picture than I drew, probably. And we can also call that a parallel anti-parallel structure. First row is facing left, second row is facing right, and so on if we were doing it in the classroom. Okay, so the next structure we're going to talk about is a triple helix. So we have 3 polypeptide chains kind of braided or woven together. Well, hang on. We said we're going to have multiple polypeptide chains later. What's the difference? The difference is this multiple chain structure is formed by hydrogen bonds between the amino hydrogen and the carboxyl oxygen. So we're being very particular about how we're forming the hydrogen bonds, not just from anything that might happen to form that attraction. It's the carboxyl oxygen and the amino hydrogen. The most common example you're going to see of a triple helix is that of collagen. The 3 polypeptide chains in collagen are going to be a glycine, a proline, the 3 amino acids, and the hydroxylated version of either a proline or a lysine. So hydroxyproline or hydroxylysine. So that's typical of collagen. You're going to see it everywhere. Connective tissue, skin, tendons, cartilage, everything. Here's where, in the context of protein structure, though, you can get messed up. It's a secondary structure. Triple helix sounds kind of 3-ish, and everybody likes to ask you, what is a triple helix? Primary, secondary, tertiary, quaternary. And they're going to see if you think, triple sounds kind of 3-ish, go for tertiary, and it's not. It's secondary. So be a little careful there. Okay, next place we're going to go is the 3-dimensional structure of proteins. So next one is the tertiary structure. And what that's doing is forming the overall shape of the protein. This gets a little bit confusing because when you think 3-dimensional, well, isn't a single atom even 3-dimensional? Yes, but overall 3-dimensional. Once we have the whole protein together, what kind of shape are we forming? And a lot of this shape comes from cross-links between the R groups. So we go back to, say, our alpha helix, we've got the R group sticking out. You remember steric hindrance, everything wants to be spread out and have lots of elbow room, so let them stick out. Beta pleated sheet, they're going to stick up, stick down, wherever to get out of the way. Again, molecules like elbow room. So then, whatever R groups come in proximity of each other and want to form bonds, cross-links, whatever, they might just do that. So if I have a couple sulfurs, I might form a disulfide linkage. Might still have ionic interactions, hydrogen bonds, hydrophobic interactions, hydrophilic interactions. So basically anything that can form will if that part of the molecule is close enough to the part of the molecule that it can form those bonds with. So a little bit of a review of general chemistry here. I won't go through it step by step with you. It's stuff you've done in Gen Chem, but I threw it in. Sometimes it's easier to have it right in front of you. Okay, so the last protein structure we're going to talk about is quaternary. So what I have going on now is I have multiple protein or polypeptide chains. So let's say here, I've got a chain, I've got a chain, got a chain, and I've got a chain. And what this molecule actually is the most common example of a quaternary structure, and that's hemoglobin. And we're going to spend a pretty decent amount of time with hemoglobin. So I've got those 4 polypeptide chains hanging out with each other. And it's the same story with the bonds. Whatever can form will form if the part of the molecule that would form that bond with that other part of the molecule is close enough to the other part to do that. That was some horrific grammar. So we have covalent, we have non-covalent. Again, basically whatever can happen will. We can have hydrogen bonds. Again, we can have ionic interactions, van der Waals, disulfide, hydrophobic, hydrophilic, whatever. So again, some of the forces, some of the bonds, and we'll come back and talk about cysteine and cysteine. And that gets kind of interesting with our sulfurs. And again, the hydrophobic part of the molecule is trying to get into water if it were hydrophilic, out of water if it were if it is hydrophobic. Okay, let's talk about something for a minute, something called a chaperone. A chaperone doesn't just work for proteins, but we're going to talk about it in the context of proteins. So here's something we do. There's a couple of disclaimers we'll keep going back to. One is that thing where we said we talk about everything like step 1, we're done with step 1, then we do step 2, like it's the only thing going on in the cell, the tissue, the organism, whatever, finish it, go to step 3. And our aha put it together moment sometimes is we have lots of stuff going on at once, very often in all different places and everything. And let me remind you with that, there's no one concept in this course that's difficult at all. None of it is. One of the challenges, though, is putting the pieces together. So the realization that, we have multiple stuff going on at once is kind of the realization that helps you put the pieces together. So with proteins, we just talked about, we form primary structure, we form secondary structure, like we're doing one thing at a time. And not every protein has everything. Well, they all have to have primary. Not everyone has everything, but as we form the protein, we're going to do all the folding at once. Whatever structures we have, we're going to form it while we do it. Chaperones assist primarily with tertiary structure formation. So what they're going to do, they're another protein that assists with the protein folding. We don't make the whole thing, then finish, then go and fold it. We fold it as we go, and chaperones assist in doing that. Okay, we're constantly, like so many molecules, turning over protein. So we're constantly making protein, we're constantly breaking protein. So we have a couple of different ways of breaking down protein. We have a ubiquitin protease mechanism. We'll talk about that a little more later, but we use it mostly on endogenous proteins. So proteins that were synthesized in the cell, we need energy to do it. So we'll talk about that. We also use enzymes. We always remember enzymes because we use enzymes for everything. And they're acid hydrolases. We don't need energy for this one, and this one's primarily on extracellular proteins. So it's the one we'll spend the most time on. We'll come back to the ubiquitin proteases. Okay, denaturing proteins. What denaturation is breaking down the secondary, tertiary, and quaternary structures. So remember we said if we want to break primary structure, that's hard to do. We're either going to use an enzyme, which we're going to use an enzyme, or we've got to raise the temperature and swing the pH. Either or won't cut it. If we want to break up the secondary, tertiary, and quaternary structures, they're easier. And depending on which one we're doing and what kind of bond it is, we have different ways of doing that. We can use heat or we can use organic solvents. That's going to break up some hydrogen bonds and break up some hydrophobic attractions. We can swing the pH, just swing the pH, not do anything with the temperature. We can break up the hydrogen bonds that way. We can use heavy metal ions. We'll talk about that more. They tend to target the disulfide bonds. Or we can shake the daylights out of it. We can use agitation, stretch the chains out until they break. And some common examples of denaturing proteins, things that you've probably done and thought about before. And let's talk about pathologies for a second. We're not really going to bring pathologies into this class. This is a normal biochemistry class, but we are going to talk about them here and there. So the other little disclaimer we're going to make is that we're going to talk about everything like it's a perfect world. We make perfect proteins in perfect ways, and that's just it. But we've already said, and let me remind you, of what pathology is. Pathology is either biochem gone bad, anatomy gone bad, or physiology gone bad. Okay, so what do I do with that? Well, here's what you do with that. If you know your normals really, really well, pathology gets much easier because you think about the normal, think about where's the disconnect in my normal, and what's the consequence of that? The consequence of that is your pathology. So, I'm not going to ask you about these pathologies, but I want you to read them and take a minute and do that. So we talked about forming primary, secondary, tertiary, and quaternary protein structure. We talked about forming these perfect, beautiful proteins. But what if we don't form perfect, beautiful proteins? Well, here's one of the things that can happen. We can misfold a protein and form an amyloid. So it's a misformed, misshaped protein. It could accumulate in specific tissues and result in things like Alzheimer's disease, result in some other degenerative diseases, all because we didn't form our protein properly. Another misformed protein can result in a prion, very similar to an amyloid. This one's probably not going to affect you much, but it's kind of interesting. It's thought to be the cause of mad cow disease. Forms this prion, which is an infectious agent made up primarily of protein, a misformed, misfolded protein, and that's the molecule that is thought to transmit mad cow disease by that molecule entering the host organism. So obviously you're more likely to have Alzheimer's patients than mad cow patients, but it's still kind of an interesting concept idea. Okay, so we're going to stop there, but let's go back and talk for a second. So let's talk about our protein structure. So we have primary protein structure formed by peptide bonds. Peptide bonds are kind of an oddball little bond in the sense that they have partial double bond character. Doesn't mean they're double bonds. They're not. Don't let anyone trick you in a question into saying they're a double bond. They're a total wannabe. They act like a double bond even though they're not. So what I mean by that is they're shorter than most other single bonds. They don't allow rotation like most single bonds allow. So that's our primary protein structure. Our secondary protein structure is in an alpha helix, a beta pleated sheet, or a triple helix, most common example of which is collagen. It's formed by hydrogen bonds between the carboxyl oxygen and the amino hydrogen. Then we have tertiary structure, our first 3D structure. That forms the overall big picture shape of the protein, very often forming it through interactions of the side chains. So what kind of bond characterizes that? Any of them, all of them. So whatever bond can form, might form, including hydrogen bonds. Fourth and final protein structure is a quaternary structure. That's where we have multiple polypeptide chains. The multi-polypeptide chains are going to become attracted to each other, join each other. Appropriateness of which word depends on which bond we're forming, by whatever bonds can form and are in the proximity of each other to allow them to form. So, primary structure has to be a peptide bond, cannot be hydrogen. Secondary has to be hydrogen between the carboxyl oxygen and amino hydrogen. Tertiary and quaternary can be hydrogen, but can be a number of other bonds. Okay, so that's where we're going to stop with protein structure. Next place we're going to go will be a discussion mostly of globular proteins, focused mostly on hemoglobin, but we'll talk a little bit about fibrous proteins also.